Hello everyone, this is a video lecture for Business Calculus, Math 1325, and we are in 9.5, Differentiation Properties. Oh, that's a big name. Anyways, derivatives is what they're trying to say here. These are derivatives. So we did a little bit of derivatives already. I am going to just give you all the goodies to this stuff, and yet I don't think we're actually going to be using it all. So nonetheless, I want to show you all the good stuff here, okay? So we have power rule, which I believe we already had or something like that. I'm trying to look through my notes. It's a whole new day today, so you know what I mean. So d dx of x to the n is equal to n times x to the n minus 1. So again, I thought we already did this, but if not, let me show you. It's very simple. If you have a power on something like x squared, and you say, oh, I want to find the derivative. The 2 comes down, and you minus 1 from the power. You minus 1, so 2 minus 1 is 1. Cool, that's very simple. We're going to do that a lot, so I just wanted to show a little mini example for that guy. Let's keep going. So we got product rule. Again, I might be overdoing it here. I don't think we actually use each of these this time, but it's still really important. You might as well learn it because it's going to come up again later, like for sure. I've already, like, just as a side note here, if I'm a little confused, it's because I've been working far ahead on the actual content of these videos, and then I come back and I'm actually just doing the videos. So I'm like already through chapter 10, and so I know for sure you're going to be using this stuff. So it's a good thing to do this now and learn it now, and then later I'll even remind you, of course. But here's the formulas nonetheless, okay? So we got a times sign. So I'm saying f times g, and it means two different expressions. And I'll give a quick example, but what it is f prime g plus fg prime. And because the plus sign is commutative, that's a fancy word there, commutative, it basically means it's like 2 plus 3 is equal to 3 plus 2. You can like flip them, and so you can flip these guys. Now that looks a little bit, fancy, let's just say, but what you're doing is you're saying one thing derivative, but you leave the other one alone, then you leave the first one alone, take the derivative of the second. So quick example, let's say that I had y is equal to x minus 1, and then let's say 2x plus 3. I'm just making something up. So we got an f, we got a g, and so when I take my derivative, I'm going to say, okay, we'll take the derivative of the first one, and this one it'll just be a 1. Basically because there's a 1 right there. But I leave the second one alone, plus sign. Now I leave the first one alone and take the derivative of the second. Derivative here is just going to be that 2. Again, there's other properties that I might be forgetting, but like the constants go to 0. Here the x basically just goes away and leaves the number, that kind of stuff. So here's your answer. You simplify, blah, 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 but that's the meat and taters of it, okay? Quotient rule. Again, I don't think that we're going to see it right now, but I want you to know it because we're going to use it for sure. And this is one of the bigger ones, okay? This is when you're taking a derivative of f over g. Now, I'm going to give you the official formula here. It's going to be g f prime minus f g prime all over g squared. There's no way you're memorizing that. It's low d high minus high d low divided by the square of what's below. See, it sounds kind of like a little nursery rhyme because it is. So you got your high and you got your low, and you do the same formula. It's great. So there you go. I'll definitely remind you that as we keep going. As far as examples go, I don't want to do it because I don't think we're doing it today. But that's definitely going to be a big guy coming up. And chain rule. There is a whole section devoted just to chain rule in chapter 10, I believe, but I'm going to show you nonetheless. So this is when you have composite functions. That is a function inside of a function. And to do the derivative of this big thing, you're taking the derivative of the outside and you leave the inside alone, but then you multiply it by the derivative of the inside. I might use this one once today because sometimes they'll give you some odd stuff, and I just think that using chain rule is way easier. So I'll probably use this one. Let's do a quick example on this guy. So let's say I had 2x plus 3, and I'm going to say all to the 4th power. and I want to take a derivative of that guy. So the 4 comes down to the front, of course, and I now leave the inside alone, and then I minus 1 from the power. It's just the same as power rule. Whatever you need to do, power rule, product rule, it doesn't really matter. But what we're doing here is the same as what we've always done. You just leave the inside alone. Except now you have to take the derivative of the inside and multiply it by. So what's the derivative inside here is a 2. And so that's the only big difference here, is that you're doing everything normal. You just kind of assume like, oh, it's inside. All right, whatever. And then you take the derivative of it and multiply. And so in this particular case, the 4 and the 2 make an 8 on the outside, and you leave the inside alone because it's way complicated. It's good enough. So there you go. All right, cool. I'll definitely be using that one here soon. So those are the big 4 that we will always be using for derivatives going forward. So let me go through some homework examples, and let's see what they have and compare it. So they also start using this dy dx stuff, and I'm going to explain it here in just a second for y equals x to the 6. Okay, so normally what we just say is y prime, and I'm pretty sure I was very prominent in that it means, this means derivative. It's y prime, and that's cool. These are the same thing. And so this thing right here is called dy, dy, and then just dx. You don't have to say over. I don't even know how to spell y and x. I know I got d, right? D. I don't know. dy dx. You don't put say divide by or anything. We just understand it because we say it so fast. Everybody understands. It's just like, oh yeah, you mean derivative. So if you ever see dy dx, it means y prime. Later, and I don't think it's going to be this chapter, but later in chapter 10, we're going to break this part down a lot more, where it's going to be a lot more important when we're doing implicit differentiation. Okay, so that's going to be a whole other ballgame, and it's really fun topics. I love working on it. And I'm just going to give you a tiny bit of math history here. This right here is the Leibniz style. Oh gosh, I don't know if I could spell his name. Leibniz. No, there's an I in there somewhere. There you go. It's the Leibniz format, I guess you can say. This is what Leibniz used, and this is the Newtonian style of derivatives. There's actually uses for both, but again, this is business calculus, so you're really not going to be too concerned about math history. They're the same. We're cool. Here we go. So if they say find dy dx, well, okay, we're just finding the derivative. The 6 comes down, and now you minus 1 from the power. You're done. That was all that problem was. But I had to give you a lot of background because it's important. When you see something, you're like, hey, what are they asking for? That's why you're watching these videos, because I tell you what they're asking for. And that's why I do the homework, so that I know exactly what you're going to be seeing, because that's important to me. Okay, so it says, hey, here's your function. Go ahead and find the derivative. And doing it like this makes me feel like I want to do quotient rule. If you go back up, and I got to say, a lot of calculus folks, and this is either way, says, oh, well, that's a division, so we must use quotient rule. No. That's very specific. If you have some really crazy stuff going on, this I can rewrite as this. Now let's pause for a second. This is just a whole new way of seeing it. I'm saying that the power is a negative because it was in the bottom. But now, when I take a derivative, I say, oh, well, the negative 12 comes down to the front, and then I minus 1 from the power. I minus 1 from the power. Yeah, I'm hitting my desk there because it's emphasizing, I guess. Minus 1. So whatever I have here, I'm not saying it's going to be 11. I'm minusing 1. What's this minus 1? It's now negative 13, okay? And, of course, negative 13, that means it's in the denominator. There you go. We're done. So a little bit of rewrite is important, okay? Next one. And again, I want to hit up all these strange-looking questions. This here is, it says f prime of 6 is equal to 8. And then it says g prime of 6 is equal to 6. And then it says h prime at 6 is equal to what? And those are 6s, by the way. They're all 6s. And then it said that h is equal to 3f plus 5 g plus 2. And this was weird. Like, this is why I want to do homework, because it just doesn't make any sense. Like, what are you asking for here? You know, it's not a hard problem, not at all. It's just strange. So they're looking for this h prime stuff. Like, forget about the 6 for a little bit. It's just the h prime. So okay, well, let's take some derivative. Now, this is where things get a little funny. It says 3 times f. Well, I'm going to take the derivative, so now it turns to f prime. I'm not kidding you. It's not that hard. It's really that easy. Derivative of f is f prime. Yeah, the derivative of g is g prime, and we already know the 2 is going to go to a 0. So here's a formula. Now they're saying, hey, go ahead and plug in for the 6 and all that stuff. Well, it's already been plugged in for us. These values are what we're going to use here and here. 3 times 8 and 5 times the 6. Like, you just, in a way, like all this 6 right here in the front, it's kind of meaningless. As long as they're the same number, you're good to go. So I put it all in, punched it in, calculator, fine. I mean, I already did it on the side here. I guess I'll just double check my work with you. Yeah, that's what I got, 54. Yay. All right. Cool. So it's not hard. It's just kind of weird. So next one, 9, 5, 31. I have y is equal to 2x to the negative 7 minus 3 times x to the negative 1. Find y prime. Again, a very simple problem, but it just looks scary. It just looks like, oh no, there's negative powers. Well, I mean, that's the same as anything else, truly. So you move the 7 down, you move the negative 1 down. So here we got a negative 14 in the front, x. And again, you minus 1 from the powers. Now it's going to be negative 8. These two negatives are going to end up being a positive 3. Again, minus 1 from the power. And this is it. And I boxed it in. I think that's the answer. Like, they don't want to simplify. They gave it to us with negative powers. I give it back in negative powers. There you go. So if you want to simplify, go ahead. Next question. 61. That's a 6. So we have y is equal to 144x minus 16x squared. And then it says we got y prime is equal to something. I got y prime of 0 is equal to something, and y prime of 1 is equal to something. And then it says find x equals blank when my y prime is equal to 0. So this is some good stuff here, but it's a little bit of a work. We need y prime. So taking the derivative, I got a 144. And then this 2 is going to come down to make it a 32x. Oh, you know what? This was some kind of word problem, I bet. So pause for a second. If this is a word problem on the homework and you're seeing me like not even read the words at all, it's because I read it and I'm kind of just showing you how to digest these things, right? There's a lot of words and word problems, but what's the heart of that problem is this math stuff that we're doing. So sometimes I'll do that, and that's okay. That's okay. I'm just showing you what to take from this. Okay, well, we're done with the first part. It said just find the derivative, so we did. And then it says, like, find it when you plug in a 0. So I plug in a 0, and I get this. And then plug in a 1, and I don't really care anymore. This one I'm more concerned about. I want to do that one. So it says, find when the derivative is equal to 0. I'm going to move this over. I'm going to divide by the 32. I think we get a nice even number here. What do we get? Nope. 4.5. Good enough. There you go. I guess I could show you. You know, it's because I have like all my papers in the front and my keyboard's like not easy to get to all the time. You might hear it like, it's because it's like uneven and weird right now. But you can't see that. There it is. There's your answers, and let's keep cruising. So next question here. Hold on. I'm trying to put all my papers in the right place. All right, there we go. Next question. You can see great editing and finishing styles for these videos, right? It's just, no, there's not. I'm just joking with you. Because I'm a real human just like you are. We got y equals this thing, find y prime. Timeout, timeout, timeout. Without me showing you chain rule, you would have had to do this the long way, and I just don't want you to because that takes forever. So what they wanted you to do is say, oh, there's two of them. And then I can like start foiling it out, 81x squared, and I don't care anymore. And then take the derivative of that. It's a long process. It's way easier just to do it with chain rule, which is good. So let's do that. I'm taking the 2, move it down to the front. I leave the inside alone, and then I minus 1 from the power. And that's our normal derivative stuff, right? You got a power, you bring it down to the front, you minus 1 from the power. Cool. Oh, but wait, I have a complicated inside. And I often use that word complicated inside because it's not just a plain x. There's stuff going on. And so if that's the case, then I need to say, well, multiply by the derivative of that stuff on the inside. That's just going to be a 9. And so then I'm going to push these two things to the front as an 18. I guess you could distribute if you like 162 plus 72. And there you go. There's your answer. So chain rule actually was way, way faster than trying to FOIL it and then take a derivative. That's why we have to know these techniques, because what if they had not a square but like a cube on your homework, or even worse, a 4 power, and like it really gets annoying unless you have chain rule. Chain rule makes it very simple. Okay, next question. So d dx, I probably didn't describe this. I'm going to talk about it a bit more of this thing, and they say equals what? Now, this, I want to say quotient rule because it looks like a quotient, right? It looks like a fraction. But I think we could do a little bit better on this one. Now, I don't think I mentioned it, and I'm just remembering now. That D, what does D stand for? It stands for derivative. Wow, really? Anyways, it stands for derivative. And I know it looks kind of funky here with like d dx and all that stuff. When you're thinking the D's cancel. No, not really. It's more like an operator than anything. But without getting into the nuancy stuff, D means derivative. So just take the derivative of this guy. Now, again, I want to say quotient rule because I have that formula now, and I got a high, I got a low, and square below, and all that good stuff. Okay, but I could do something way better. What if I were to split it up? Like, as in, they both get an X in the bottom individually, something like that, and that's fine. These x's actually cancel, so that's nifty. And we're left with this guy. I want to go one more step because I can, because I'm the teacher. I can. No, it's anybody can. Just making it fun for just a second there. There you go. Notice that it was in the denominator, so I'm going to have a negative power, and that's a -1 because there's a 1 over there. Now I can take the derivative of this so much easier. And notice that I have been keeping my equal signs the entire way through, okay? Because when I take this derivative, it is going to be equal to what I was been saying this whole time. So that's kind of nifty. 100 goes to 0. 30 stays in the front. A -1 comes down to the front. And then I minus 1 from the power. I minus 1 from the power. So now it's -2. This is the entirety of our answer. So -30 over x squared. We are done. That was it. So kaboom. Is this the last question? I think so. Yeah, this is the last question. Okay, cool. I noticed because it's like one of those application questions, which is good. I mean, it's good to have application questions, and they're normally at the very back anyways. This one's not... this one's not too bad. Some of them get kind of annoying, but this one's cool. Like, the purpose of application questions... That's not producing, that's produced. Anyways, the purpose of application questions is to have you see and apply this math in different scenarios, and your application of this math will be all kind of different things going forward. I mean, your boss might tell you to this, or you might need to go and do that, blah, blah, blah. I don't know. You don't know. But if you train yourself on some of these things, you can at least say, you know what, there might be a way. I think I might have the tools if I just... So, and let me show you a perfect example of tools, okay? So we have all this data, and each year, I think it's limousines or something, these are the amount of limousines produced. And it says they want a cubic regression model. Cubic regression, okay? The regression part means best fit line, and line is a could be a squirrely line. Cubic means it starts with x cubed, blah 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 blah. Okay, so we got an x cubed, blah 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 blah, and we want it to fit the best thing here. One last thing is x is years after 1980, and that's just to make it easier on the model. All right. Oh, and then we're going to take the derivative of that here in a second. So, what is going on? So let's just say for a second, I'm just going to rough graph this thing. We got 3,000, 6,000, 2,000. You know, it's all over the place. And so we got, and again, these are years after 1980. So technically, I don't want to use these. I want to use 0, 5, 10, 15, and 20. But regardless, I'm going to just rough graph some of this stuff, and it looks something kind of like this probably. There you go. And they're saying, okay, we got all these data points, and I want you to do this x cube thing. And an x cube looks kind of like this. So I want to go like a wampa whoosh. So here we go. There you go. And it's not perfect, and that is fine. You can't get it perfect most of the time, but you can get it pretty close. And so there'll be a little bit of variation in there for each of these points. Sometimes it might hit right on, sometimes it won't. But there you go. That's my best fit cubic wampa whooshy thingy. How the heck do you find that? And if you read the instructions for this problem, it says use a graphing calculator. And this is exactly why you're watching the video. So I could show you how to use Desmos graphing. So pay attention, because this is it, okay? I need to make a table. And so right here, add item, table. And I need to put in all those values that I have right there. So the 0, the 5, the 10, the 15, and the 20. And then I'm going to put it in the y values next to them. 3,000, 6800, blah, blah, blah. 3800. Okay, good. Now, before I keep going, this should show up here somewhere. And if you scroll out, again, we're talking like in the thousands and stuff. There they are. That does not look good. And it's because we only have these small numbers here, and these are going to be really big numbers. I'd have to like change the scale to make it look better, and I will. But you don't have to do what I'm doing at this point, okay? This is just Chad going rogue on you here. So let's do 25, 0 to 25, and you can see that's a lot better looking. It's definitely not perfect. You can see there's a point right here, actually. And so it's going to like wampa whoosh like that. Here's how you get the actual answer. So we have this table, and notice it says x1, y1. It has to say that. If not, you like refresh or change what you're going to type here in a second. But I need to type in the regression model. And so this is what it looks like, y1. And how I got that is I literally just typed a 1. I didn't have to, you could subscript and then 1. Subscript with this would be shift minus sign. You don't have to do that, though. You just click 1, and it just does it for you. Don't put an equals. Put a tilde. That's telling Desmos that you're doing a regression model. Again, a best fit line. A x1 cubed, b x1 squared, c x1, and then plus the d. That should account for everything. And look, just like I said, look, did you see it? Look at that. Pretty darn good, Chad. Pretty darn good. I mean, it's not perfect, but that's the point. It's pretty close. Pretty close. This is the style, the format that you need to type in there. Okay? Scroll down, and it gives you all the numbers you need. And so we had chosen A for the first number, B, C, D, all that kind of stuff. And so these are the answers that we need. Like literally, I'm just going to start writing it. So y equals, I got 5.6x cubed. B is a negative 176x squared. 1400x, and then finally 3100. There you go. All right, this is your answer for your homework. Okay. Now, one other thing, since we're on the topic, because I can't ignore it. You see this r squared right here? That's telling you how good a fit it is. You can kind of think of it like a percentage of goodness of fit, and so it's kind of like saying 91 or 92% good. And if you got a 92% on your exam, that would be good. So good thing. So if you get this number that's like 70, you're like, you get it like a 50, and you're like, you get it 30, and that was a totally not working at all. So that tells you how good the model is, and you can just zoom out and see it's pretty good. I mean, it's not perfect, but it kind of hits the idea of the points. Therefore, we're calling it 92. That's an A. We love it. Okay, last part is that they now want you to find the derivative of this. That's super easy at this point, really. So the 3 comes down. 3 times 5.6 is 16.8. Now it's x squared. The 2 comes down, still a negative 352x. I'm just copying what I got. And then the x goes away, and then that number just goes to 0. So there you go. There's my derivative. And now we're done. We're done with that section. Thank you very much, and have a great day.